We will now look at the role operational amplifiers play in interfacing circuits. Amplifier and filter gains are frequently expressed in decibels, named after Alexander Graham Bell. The decibel is an expression on a logarithmic scale of how much greater or smaller the output is than the input. The equation for decibel voltage gain is AV in dB is equal to 20 times the log of AV, where AV and dB is the voltage gain in decibels and AV is the straight voltage gain. As an example, an op-amp design has a voltage gain of 5,000. Find the voltage gain in decibels. The solution: apply the equation for the decibel voltage gain. AV dB is equal to 20 times log of AV. 20 times log of 5,000 is equal to 74 decibels. The amplifier voltage gain expressed in decibels is 74 dB. Another example: an amplifier is said to have a voltage gain of 45 dB. Find the straight voltage gain. The solution: rearrange the equation for decibels and solve for the AV. The straight voltage gain of the amplifier is 178. Using the observations from the table, we end up with the following rules. Factor the straight voltage gain into multiples of 10 and multiples of 2. And for each multiple of 10, add 20 decibels. And for each multiple of 2, add 6 decibels. This example shows how we can use that shorthand. An op-amp design that we looked at before has a voltage gain of 5,000 volts. Estimate the decimal gain for the amplifier. The solution is: the straight voltage gain is 5,000. The first thing we do is factor 5,000 into multiples of 2 and 10 as best we can. So we note that 5,000 is 5 times 10 times 10 times 10. Also notice that 5 is almost 4, which is 2 times 2. So we could say it's equal to 2 times 2 times 10 times 10 times 10. Now we add 6 dB for each 2 times and add 20 dB for each 10 times. So we get 6 plus 6 plus 20 plus 20 plus 20 is equal to 72 decibels. Notice that our estimate of 72 decibels is pretty close to the actual answer we worked out before, 74 decibels. This is just a simple way without using the log functions. From the previous example, you can use this procedure to estimate the straight voltage gain from the decibel gain. Break up the decibel gain into the closest match of the two addends of 6 and 20. For each addend of 6, multiply by 2. For each addend of minus 6, multiply by 0.05. For each addend of 20, multiply by 10. For each addend of minus 20, multiply by 0.01. Using decibels makes it easier to calculate the overall gain of a system. A signal may have to go through many modules on its way to its final destination, and each module could act as either an amplifier or an attenuator. If you know the decibel gain for each module, all you have to do is add them up to get the overall gain. Straight gains have to be multiplied. The example of a directional antenna is shown. The signal goes through 4 modules, each with its own gain or loss, but the overall gain is easily calculated to be 15 decibels. Active filters. Filter circuits either pass or stop signals depending on frequency. This slide shows the responses of some basic types of filters. The low-pass filter, in figure A, allows only frequencies below the cutoff frequency Fc to pass. Frequencies above Fc are attenuated. The actual cutoff voltage is defined as the frequency where the gain drops to 0,707 or minus 3 dB of its passband value. The steepness of the attenuation depends on the type of filter. A common single-stage RC filter, described in the next few slides, decreases the signal by a factor of 10 each time the frequency goes up by 10 or minus 20 dBs per decade. The high-pass filter, figure C, passes signals with a range of frequencies between FC1 and FC2 and rejects all others. The notch filter, figure D, rejects only a narrow range of frequencies and passes all others. Some of these filters are particularly useful for signal conditioning in control systems. For example, sensors reporting such things as temperature or flow rate have relatively slow changing signals. A low-pass filter would allow the sensor signals to pass while rejecting higher frequency electrical noise, as from motors or relays. The notch filter is also particularly useful. It can be used to attenuate a particular noise or frequency, such as the 60 Hz from electrical mains. Theoretically, filters can be constructed entirely from passive components, resistors, capacitors, and inductance. In practice, such filters tend to change characteristics when inserted in a circuit because the impedances interact. The op-amp can solve this problem by providing impedance isolation between the filter and the circuit it's driving, and provide some gain as well. A filter using an op-amp is called an active filter. This diagram shows a single-stage low-pass filter incorporating an op-amp. Notice that this is basically a non-inverting amp with an RC filter connected to the input. The performance of this filter can be described with equations for gain and the cutoff frequency. As shown. This slide shows a single-stage high-pass filter. It is similar to the low-pass filter, but the positions of the resistor and capacitor are reversed. The equations for the gain and cutoff frequency are exactly the same as for the low-pass filter. A band-pass filter can be built by cascading a low-pass filter with a high-pass filter together. The cutoff frequencies of the low-pass filter, FC2, must be higher than the cutoff frequency of the high-pass filter, FC1. The lower diagram is an op-amp notch filter. The filter itself is a Wien bridge type. The gain of the signal is 1 at the frequencies except near the notch. The frequency Fn, which is suppressed or notched out, can be calculated from the equation Fn is equal to I over 2 pi RC. Again, the equations Fn is 1 over 2 pi RC. A number of special purpose circuits are useful in certain applications. We will look at the most commonly used circuit, but beware there are others, and these are covered in the text but not in this course. Most signals are voltage signals, which means that the information being conveyed is proportional to the voltage. Two potential problems with this can arise. Susceptibility to electrical noise increases, which is usually in the form of voltage spikes, and any resistance in the signal wire causes a voltage drop. For short distances, wire can usually be effectively shielded from noise and voltage drops and are not a problem. For longer cable runs with numerous connectors, such as might be found in a process control system in a large factory, noise and total cable resistance may become significant. This diagram illustrates this situation. Notice that the signal from the sensor has been greatly diminished by the cable resistance. The diagram does not show the effects of noise, but the signal will become dirty, meaning it won't be a nice clean sinusoidal signal emanating from the source by the time it reaches the receiver. One solution to the problems of noise and signal attenuation is to use current instead of voltage to convey the information. This is effective because current, unlike voltage, is not as susceptible to noise and does not drop when it goes through a resistance. As Kirchhoff's current law tells us, whatever current goes into a branch comes out. This is illustrated in the diagram. Notice that the signal emerges from the source, travels to the receiver, and then loops back again to the source. The receiver does not siphon out any current, but merely senses it. Therefore, we have a current loop, which goes from source to receiver and back to source. Any resistance in the wires cannot alter the fact that the current remains the same throughout the entire loop. If most of the transducers produce a voltage signal, how do we convert that information to a current signal? Well, since this is a chapter on amplifiers, there should be no surprise that op-amps play a role. Op-amps can be used to implement both the transmitter and the receiver in a current loop system. This diagram shows a transmitter circuit. The circuit converts a voltage signal Vin into an output current Iout, which is proportional to Vin. The op-amp circuit causes the output current to be independent of any resistance in the line. It accomplishes this by automatically increasing or decreasing its output voltage Vout in response to any increase or decreasing line resistance. The explanation for how the circuit works is as follows. Recall that for an op-amp, we can assume V1 is virtually the same as V2. Therefore, the voltage across R must be Vn. Applying Ohm's law to R, we get IR is equal to Vn over R, where IR is the value of the current in resistor R. The source of IR can be the negative input of the op-amp, so it must be coming through the loop. That is, IR is equal to Iout, which we see is equal to Vin over R. Thus, the loop current is dependent only on the input signal Vin and the resistor R, and not by any line or load resistance. Once the current signal gets to the receiver, it needs to be reconverted back into a voltage. In other words, the receiver is a current to voltage converter. A resistor is the most direct way to convert a current into a voltage. But we have a special problem here. We have to detect the voltage across the load resistor without knowing where this voltage is with respect to ground. Consider the complete current loop circuit shown. The receiver resistor Rrec is floating, that is, neither end is grounded. If we ground the bottom of Rrec, current can escape from the loop and the whole concept will fall apart. The problem is solved by using a differential amplifier as the receiver, as illustrated. The differential amplifier samples and amplifies only the voltage difference across the receiver resistor. The differential amplifier must be designed to have a high input resistance to prevent any significant amount of current from leaving the loop at the receiver. The output of the differential amplifier is a single-ended voltage that can be referenced to ground. By crunching the numbers, and you should do so to check with your understanding, we can show that the output voltage Vout is dependent on the loop current, receiver resistance, and the differentiator gain. The current loop technique is one of the industry standard methods of converting controllers to sensors and/or actuators. The standard system specifies a current range of 4 to 20 milliamps, where 4 milliamps corresponds to the minimum signal and 20 milliamps corresponds to the maximum signal. For example, if a sensor puts out a signal in the range of 0 to 5 volts, then 4 milliamps is the current in the current loop would correspond to 0 volts from the sensor, and 20 milliamps would correspond to 5 volts. The non-zero minimum, 4 milliamps, is used to detect circuit opening and to minimize the effect of electrical noise. If the current is less than 4 milliamps, then the assumption is that something has failed, possibly a wire break. Transmitters and receivers in the range 4 to 20 milliamps are available in IC form. And most transducers, analog transducers, will be a 4 to 20 milliamp signal. Thanks for watching.